Postgres Foreign Data Wrappers, or a way that your database can talk back to your services. And someone's run off, that's all right. Yeah. Can you click on it, Bed?
Oh, yes. Allow it full screen. That's right.
Yeah, allow.
Oh, allow. Allow.
Yeah.
Okay.
Cool. Okay. Contents of this is going to cover, the basic approach of querying from a language, which I'm sure you're all familiar with. We'll then move to how your data can span multiple databases, and you end up querying them from your application. Then we're going to talk about how that complexity can be pushed into the database and when this is appropriate. The foreign data wrapper section will be the largest, and that will cover how you actually implement this ability for the database to talk to other services. And then we'll talk about generic services. So I'm going to use Python for the examples just because it's so quick and easy, and so you can fit it on the screen. And here we can see that you're just making a query to a database as you normally would. Now, if you're writing a simple application, you might use an object relational mapper, and that would allow you to define your database records in terms of objects, and then your use of them can practically be invisible. And if you get really into that, then you can even forget you're using a database at all. Now, as your data grows, and your application changes, you're going to have needs which aren't met by your current database. Basically, you need it to be faster. You're always going to need it to be faster. So what's the problem? Well, when Postgres runs a query, it only uses a single CPU. So if you're doing a really taxing query, it can take a long time. If you're clever, you can split the query up into multiple parts that can each be executed separately. But there's a few problems with this. If you execute multiple separate queries, they can have different transactions, and there can be changes in between the transactions. So you need to synchronize those transactions to make sure you have a consistent view of the database. Now here, I haven't actually done this inside a language that you might use, just to show you what the actual underlying SQL commands that you would execute are. So in the first example, we've got the master transaction, which exports an ID of the transaction. And then we use the slaves to synchronize to that. Now, the problem with this approach is that most queries have overlapping parts that would have to be computed again and again, such as joins. So splitting your transaction in this way is very difficult. Postgres comes with a tool called pgdump, which actually uses this technique in order to dump each table separately, but in parallel. And if you've got something like that that's easily divisible and separate, then you can use this approach. But I'm sure by now you've figured out that it's actually quite difficult to use this correctly, and there are very few cases when it's appropriate. Instead, what you should do is push this complexity into the database. The database can then execute your query in a simple fashion from your app's perspective, but all of that additional logic and smarts is inside the database. Now, in the case of using multiple CPUs, you might use an extension such as parallel aggregation, which would allow you to more fully use your computer to process the query. Now, I'm sure that if you've got a DBA or someone similar, they could teach you how to write more efficient queries. And this approach is also very valid for making your queries faster. Now, eventually, your data is going to grow so much, or your queries are going to become so specific that the database does not meet your needs. If you think about it, the way you lay data out on a disk introduces limitations as much as it frees you. So there are always going to be situations where a certain query is going to be slow against a certain kind of database. And that's because the database is optimizing for other use cases, which can be fast. Now, in this case, you're going to start thinking about using multiple separate databases. If you use a tool that is appropriate to your task, you'll find that your queries are far faster. But now you have a problem in that you have multiple separate databases and you need to coordinate them from the application. If you think about this, this is much like splitting a single query into the single threads. Your app has to coordinate far more. And this is the kind of complexity that you want to free your app from. If you could issue a single query that joined all of these databases and returned just the data that you wanted, then it would be like your database was as fast as possible and your query remained simple. So Postgres is the perfect mediator for this. Postgres is a relational database. It happens that your different data stores relate to each other. Since this relation is how you're going to be joining those bits of data, you may as well do it in a relational database. Now, foreign data wrappers are how you can do this. In a normal database, a table contains data. You insert it, update it, delete it, and then query it using your SQL. Now, it happens that foreign data wrappers are tables which execute methods instead of operating over fixed data stores. These methods allow you to do anything you feel like. But of course, in order to be a table, you should behave like a table. So Postgres is written in C. C is pretty fast, but it's quite a disciplined language. You have to manage your own memory. A lot of safety is removed compared to other languages. The Foreign Data Wrapper API is also written in C. And so if you're really going to implement a very fast foreign data wrapper, you have to write it in C. Now, this is the rough process that you go through in order to query a table. I'm going to go into this in more depth, but basically it's split into two stages. If you've been to the previous talks, then I'm sure that you understand more about how planning works. And basically, it's split between planning the query and then executing the query. Now, the problem is that your foreign data sources often have a very different structure to your Postgres database. Now, that means that the way in which you query them is also very different. Instead of trying to map the approach of querying them to an actual table, you can use a where clause against a pretend column or a virtual column just to pass information into your foreign data wrapper. You'd map all of the columns that actually exist normally, but this would be an additional column or even more than one where you can have constraints over it which end up being queries against the foreign data wrapper. Now, the important thing to realize here is by default, Postgres will check the where clause. This means that if you do complex comparisons such as like or greater than or less than or anything like that, it's going to be difficult to ensure that all of your rows meet that constraint. If you just make it a simple equality check, then you have a very simple time of ensuring that your rows match. All you need to do is take the qualifier, which in this case is a Solr query, and add it to the rows that you return. And then you can be sure that every row meets your constraint. Now this is the query planning stage. It starts by getting the relation size. This is an estimate of the total number of rows in the query result. This is the number of rows and the average row length. This information is used to plan how this data will be joined with other data, such as if it is a very small number of rows that you're going to return, then a nested loop could be appropriate. But if your data set is going to be very large, then a nested loop would take a long time to execute. And so it's very important that you get your relation size correct. While it's important, it's not the end of the world if you don't. So after you've got the relation size, you then move on to the paths. Now it happens that the remote data source that you're querying can be as complex as Postgres, because, for example, there is a Postgres to Postgres foreign data wrapper. And when you're querying a complex remote data source, you can have multiple ways to get the same set of rows. When you have multiple ways, such as that, you can return multiple paths, each of which have different trade-offs. It would then be up to the Postgres query planner to select one of them. The most important difference is that you can have join paths. Now, these represent times when you're querying multiple tables from an individual foreign data wrapper. When you are doing so, you can actually perform the join on the remote side and return only those columns which are needed by the larger query. Obviously, this is much more efficient than querying each table separately and then joining them in Postgres. Once you've selected the path, it moves on to the plan where it provides the path it has chosen. In this plan, you should do any appropriate preparation for your query. It's important to realize that there will be additional stages before you actually execute the query. So doing things such as opening a connection to the remote data source is not appropriate at this time. Now, here we have a division between the different kinds of queries that you can do. And it's important to realize that updates and deletes first scan the table in order to select the rows that will be altered. And then they provide those rows to the alteration methods. Since this happens, and since your query may not select an appropriate unique identifier for a row, it is very important that you alter the query in order to add an appropriate ID for every row that will be altered. Otherwise, you could have a delete, which is supposed to delete one column or one row, and it actually deletes hundreds or thousands because you didn't have an ID that you could use in order to delete it. It's also possible to modify the plan if you have special needs that you need to set up in advance of actually performing the modification. So here we've got scanning, which is a lot simpler than planning. All that happens is it begins, at which point you can perform your query. Now, it's up to you if you perform your query in its entirety right at the beginning. If you do that, it can seem a lot faster when you're selecting an entire table's worth of data or something like that. But if your overall query limits the overall number of rows that are returned, then you could select a large block of data, which is then thrown away. Instead, you can just select a small amount of data and then move on to the iteration stage. Each call to iterate will return a single row. If it returns null, then iteration is complete, and you will move on to the end of the scan. But obviously, iteration gives you a chance to batch your requests to the foreign data source and then start returning the rows from the batch. And in this way, you can have a foreign data wrapper which provides a number of rows quickly and then the entire data set over time. Now, for reasons that aren't entirely clear in the documentation, I should mention that it's possible to restart the scan, but I don't know why that happens. Hopefully it doesn't. But this end state is the point at which you would free up any long-running resources that you have used. Now, it happens that in C, memory allocation is often quite troublesome. Postgres provides palloc in order to allocate memory, which will automatically be freed after the query is complete. So memory management is not too much of a concern. Now here we have alterations of tables. As you can see, this actually includes both planning and scanning depending on what you are doing. So first, the plan occurs just like when you're scanning a table. And then, let's say we were inserting rows. Now, since insertion of rows doesn't depend on the existing data in the database, it doesn't have to worry about adding a target to the scan or scanning the remote table. It can just run through each row, inserting it, and then move on to the end. Once again, you're able to cache the rows that you're inserting and then insert them in the end instead of the beginning, as you would when you were scanning. And this allows you to batch your requests. Now, if you were to alter by updating or deleting, then the first thing you need to do is to scan the table in order to find the rows that you are about to change. Now, we have this add target callback, which is the perfect point at which to add a unique column which identifies the row, such as its ID. And then the scan is performed, and you are provided with the rows that have been received from that scan in your update or delete methods. Once those methods are complete, you move on to the end, which allows you to free up any resources associated with your modification. Now, it's important to realize that for updates and deletes, the scan is complete, as in it also calls the end method, but that's an end of scan, and in this case, it's an end of modify. So don't free up anything that you might need to use for modification. Now, it's not enough just to be able to implement these methods. You need to have an actual table to query. And you do that by using create foreign table. Now, if I was to write out the SQL involved with this, it would be rather large, because when you create a table, you're creating a large data structure. The documentation for create foreign table is quite thorough. So if you're interested in this, I encourage you to look it up. The important thing to realize, though, is that it has options. These options are provided to your foreign data wrapper, and they can be anything you choose, such as the host, the port, username, password. Now, creating one table is great, but what happens if you have an entire data source? You want to create lots of tables, and that can get quite onerous quite quickly. In the latest version of Postgres, create import foreign schema has been provided. And this is a method which merely needs to return the strings which contain create foreign table statements. And in that way, you can create all of the tables that you need to use for your foreign data wrapper. Now, you can analyze the foreign data. This allows you to provide far more accurate estimates of the foreign relation size. Now, analyzing is a process where up to 10,000 remote rows are requested, along with statistics for the table, such as its total size. These 10,000 rows are used in order to calculate distribution statistics regarding different distributions of data. It's possible to hook into this data at the point at which you're getting the foreign relation size. And so you can provide the analyzed data back as your estimate. And in that way, you don't have to query your foreign data source in order to have a reasonably accurate estimate for the size of a given query. Now, C is hard work. Like I said, C is always going to be the most performant solution, but if you want to create a foreign data wrapper quickly, or if the speed of the code is not going to be your primary concern, then perhaps you could use another language. Other languages have implemented layers on top of the C API in order to make your life easier. One of them is Python. Now, Python's foreign data wrapper API is called Multicorn, and it's well documented, so it should be easy for you to implement a foreign data wrapper, and you should find it much quicker and safer than implementing it in C. But of course, it's going to be slower than the C equivalent. Now this is a complete foreign data wrapper written in Python. It's a bit of a joke, because all it does is return 20 rows where each column has the current row number. But given that Python is so incredibly terse, you could implement an actual foreign data wrapper with only a small additional number of lines. Now, the Python multi-corn API is not complete, and what it lacks is analyze. So there's no way for your estimate to hook into the previous statistics that you have gathered unless you go and do that yourself. But then you'd basically be implementing a database for yourself, which would be a bit silly. You're not going to get any callback related to a modification. So if your foreign data wrapper supports modification, you should be sure always to select the unique identifier for any row that you return. It's completely fine to do this because if you return more columns than Postgres requires, then it silently discards the additional columns. Now, there's no way to provide join paths, so each table is always going to be queried separately. And finally, there is no way to disable the check on a where clause, so you must be sure that every row that you return always contains a column that satisfies the where clause. And it's just easy enough to add in the qualifier to the columns. Now, like I said, C is always going to be the fastest foreign data wrapper API. Python can provide you with a very quick way to implement a foreign data wrapper so that you can evaluate if it is appropriate for you. Secondly, you should think about if the code that you are writing is really the slowest part. In many cases, your network round trip is going to be significantly longer than the difference between Python and C. And if that is the case, then you would not gain a great deal by switching to C, but you could have far more risk in terms of being able to crash the Postgres process, which would be quite undesirable. Now, we get on to services. If you think about it, your foreign data wrapper has the access to all of the abilities that the language provides. And this includes making arbitrary requests to arbitrary services. Now, if you think about it, a REST API is a lot like a database. It supports reads, writes, updates, and deletes. And it doesn't stop there. You could implement Twitter as a foreign data wrapper. You could implement website crawling as a foreign data wrapper. Giphy could be a foreign data wrapper. Anything you like. So these can all be tables. When you're writing foreign data wrappers for your services, you're going to end up with a few problems that you normally wouldn't have with a database, such as authentication. Now, Twitter, there used to be a foreign data wrapper for Twitter, but it no longer works because Twitter now requires authentication for all of their calls. If you wanted to provide such data, such details to your calls, then there are several ways in which you can do it. You can provide the username and password for this remote service when you are creating the table, remembering, of course, that the options that you provide to your table are for your use only. So you can provide anything you want. The problem with this is that anyone who is able to view the create table statement for your table is able to view these credentials. So you may want to do it per query, especially if you have multiple accounts which you can use to access the remote service. Finally, and if it's really sensitive credentials, you may want to implement a local service which you query instead, which can then connect to a trusted store of credentials. But obviously, that would be quite an extreme case. Secondly, we come to rate limiting. Now, when you're making queries against a database, those queries are blind to each other. So there's no way to coordinate the queries such that they don't hit a rate limit. If you think about it, if you were to do such a thing, you'd be slowing down your database queries so that you can meet the needs of an external service, and that may be very undesirable. Instead, what you can do is you can make the data available within the local database and then query against that. Now, broadly speaking, there are two ways you can do this. A materialized view can be refreshed periodically, and this will provide you with a snapshot of the data at a specific point in time, ideally quite frequently updated. It's important that when you update this, you do so concurrently. Otherwise, the update process holds an exclusive lock over the table, and that would have the same drawbacks as hitting your rate limits. The second option is to periodically copy data from the remote service into a local table. Now, this is more beneficial when you want to view historical stats, because there's no requirement for you to delete those old rows. So if you're doing a stock ticker, for example, then this historical data can be very valuable, and you might prefer to use this approach. Now, obviously, it's very important that you periodically refresh this data, whichever approach you use. Now, as I mentioned, you're able to change these remote services by issuing queries or issuing updates against them. So foreign data wrappers are tables in every sense of the word, and they are completely legitimate as targets for triggers. So if you have a caching layer in front of your website and you can associate entries in that cache with entries in your database, then as those entries change, you are able to use a foreign data wrapper in order to invalidate those cache entries. And I'm sure that you can think of many other ways in which you can update foreign services as your local data changes. And this allows you to keep everything in sync, invisible to your app. Now, you've got the full power of the language available to you. This means that you can implement anything you want in your foreign data wrapper. If you put a bit of effort into it, you could have a website running inside Postgres. I don't think that would be a good idea, though. You want to aim to have foreign data wrappers that make sense and that you can maintain over the long term. So it's important when you use this technique to ensure that you are doing so for the right reasons. Every time I find a new tool, I'm tempted to use it on everything I can. This is usually a bad idea. And so I just add a tiny word of caution here to your adventures into foreign data wrappers. Now, questions? Cool.
As well as when you are the mediate as well?
Right, Postgres